Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great honor and pleasure to welcome EUSEBIO GARDELLA, who used to be from Uruguay and now is from Sweden. And he will tell us a very fascinating story about classification of cross products. The song is yours, take it away.
Yeah. Thank you very much, Piotr. Thanks for the invitation. I was in Warsaw a few weeks ago, actually. It was super nice to be there. This time I have to give this talk online, but it's even nicer because then more people can attend. Right, so I will be talking about cross products and their classification, and I want to start by motivating this talk with the statement of a theorem. It is this one, the classification theorem, which in this form is from 2015, roughly, and it is actually very difficult to attribute it to any list of authors, because really a lot of people have contributed to it. So what one usually does nowadays is one says that this is the work of many hands, and although I'm personally not a huge fan of this expression, please forgive me that I will not start listing names, because there's always a risk, and so also the certainty that I will leave someone out that feels like they contributed as well. So it's really a lot of work put into this theorem that goes as follows. Let A and B be simple, separable, unital, nuclear, C-star algebras, which satisfy the UCT, and absorb the so-called Jiangsu algebra. So, Jiangsu algebra curly Z tensorially. So these are the assumptions. This is the class of C-star algebras that we look at, and then the statement, or what is true about them, is that A and B are isomorphic if and only if their Elliott invariants are isomorphic. Okay, so this is a statement. I don't expect necessarily every term to make sense to everyone. So let me just say a few words, although this talk is not really about this classification theorem, but rather about verifying that some C-star algebras fall within the class that is described in this theorem. Now, let me nevertheless say a few words about this thing. Simplicity just means that there are no non-trivial two-sided closed ideals. Separability is the existence of a countable dense subset. Unitality is the existence of a multiplicative unit. Nuclearity, it's the completely positive approximation property, can also be characterized in terms of tensor products. So, for example, A is nuclear if and only if for every other C-star algebra C, A tensor C max and A tensor C min, maximal and minimal tensor products agree. So the canonical map from the maximal to the minimal is isometric. That's nuclearity, or at least one way to characterize it. Satisfying the UCT. So this condition is a bit more difficult to define, and I will not do it explicitly or not in all detail. If you know KK theory, this is the same as being KK equivalent to a commutative C-star algebra. I honestly don't want to say too much more about it, because for two reasons. First of all, it is conceivable that separability and nuclearity together imply the satisfaction of the UCT. So this is an open problem. It's one of the biggest open problems now in this field of classification, whether the UCT is automatic for separable nuclear C-star algebras. That's the one thing. And the other reason why I will not discuss the UCT very much is that for the C-star algebras that I will be looking at in this talk, the UCT is automatic. So there's really nothing to worry about. for the class that we will look at. Of course, it's a major assumption in the theorem. To prove it, you absolutely need this. Finally, I want to discuss, oh, sorry, I didn't leave it much. I want to discuss a bit the Jiangsu algebra, because this is actually more central to this talk. The Jiangsu algebra is, you could say it's an infinite dimensional version of the complex numbers. It's an infinite, and now when I say infinite dimension, I mean just linear dimension as a vector space of the complex numbers. So it's an infinite dimensional C-star algebra that has the same K-theory as the complex numbers and the same trace space as the complex numbers. The trace space of the complex numbers is a point. The K-theory of this complex numbers is Z and 0. I guess the point that I'm trying to make here is that at the level of the Elliott invariant, which is essentially K-theory and traces, Z cannot be distinguished from the complex numbers. Its construction is rather delicate, and I will also not present it in detail, or at all, actually. I would just assume the existence of such a thing. The C-star algebra has this property that actually is very connected to classification now. Satisfies that the Elliott invariant of a C-star algebra A is isomorphic to the Elliott invariant of its tensor factor, tensor product with the Jiangsu algebra. Now let me add a footnote here. We are not including the order on K0 as part of the Elliott invariant for this claim, and also not for the statement of the classification. Otherwise, one has to be a little more careful with that statement. And the last thing that I will tell you about the Jiangsu algebra is that it is self-absorbing. And in fact, it's self-absorbing in a strong sense. This is called strongly self-absorbing, which implies that it's also isomorphic to the infinite tensor product of it with itself. Let me zoom out just for 1 second so that the whole thing becomes visible. So the class of C-star algebras that the theorem covers is, I hope now, more or less explained. I realize that the construction of the Jiangsu algebra, I have not given it, and perhaps it's a little of a mysterious object for now, but bear with me, otherwise it's not possible to cover everything. Perhaps it also helps to say that it's a very good C-star algebraic analog of the hyperfinite to one factor. That is not a UHF algebra. And finally, the Elliott invariant of a C-star algebra, I briefly said it verbally. It is essentially, in quotation marks, it's equal to K-theory and traces. There's also a pairing map that one has to take into account. Yeah. So this is a statement of the theorem. I mean, algebras in this class can be distinguished or identified simply by using this Elliott invariant, which one has a lot of tools to compute it, actually. For K-theory, computations of K-theory, we have a lot of tools, 6 terms exact sequence, tensor over Kulescu if it's a cross product. There's really a lot of machinery developed for that task. Computation of the trace space, well, depends on the situation that you're in. If you're lucky, there are no traces at all, then it's purely infinite. if you're slightly less lucky, then there's a unique trace, and then the trace spaces, of unique trace C star algebras are obviously the same. So depending on the situation, the computation of the trace space may be more or less difficult, but in principle, this turns a very difficult problem of finding an isomorphism between C star algebras into a, at least in practice, often easier one, which is identifying invariants.
Can I ask, it's Dabrowski, can I ask a question?
Of course.
Can you hear me?
Yeah.
So what does it mean, isomorphism of Elliott invariant A to Elliott invariant B on the level of K-theory and traces?
Yeah, this is a very good question. So it means that the K groups are isomorphic. It means that the trace spaces are homeomorphic, affinely homeomorphic. And it means that these isomorphisms that I just told you that they should exist are compatible with the pairing maps between traces and K0.
Okay.
So it's isomorphism of all of the objects involved that are compatible with a certain map between the objects involved.
Okay. Thanks.
You're welcome.
May I have a question?
Just a follow-up question. Okay.
I have a question about omitting this order on K0. Which assumptions allows you to forget about this order?
Z stability.
Z stability, okay.
Yeah, because the order, if the algebra is Z stable, the positive cone you recover as all the elements that give you have a positive image under all the functionals. So you can recover intrinsically, assuming that it's Z stable.
So just a quick question. So this isomorphism of this Elliott invariants need not come from an actual map between sister algebras, yes?
In fact, the statement of the theorem does not tell you that, but the proof actually does tell you that it comes from an isomorphism of the sister algebras. Yes.
Oh, okay.
Yeah. So they're all realized. There's perhaps one usually calls this like strong classification when the isomorphism of the invariants is realized by an isomorphism of the.
Okay, but to be precise, in the definition of this isomorphism of Elliott invariant, you don't assume this, yes?
No, right. And so in the definition of the Elliott invariant, it's just isomorphism of groups, isomorphism of spaces with some compatibility. It doesn't have to come from a map from the algebra.
Okay,
No.
Okay, thanks.
Yeah, you're welcome. And this is actually very, very important because in practice, if the invariants are very small or very tractable, or perhaps they vanish, usually sometimes they vanish, some of the groups or the trace space perhaps is empty, then it allows you to reduce isomorphism of the algebras to a very easy kind of checking. In any case, the talk is not really...
Sorry. May I continue this question? Are there known some examples of star homomorphisms between these algebras, which is it true that if you have some abstract homomorphism of such structures of this Elliott invariant, is there some class different from maybe wider than isomorphisms for which you could deduce that it is induced by this map star homomorphism between sister algebras? For instance, if you have some kind of retraction on the level of the Elliott invariant, does it imply that you have some retraction on the level of sister algebras? Actually, yes.
I don't know this. I must admit, I'm not really the right person to ask. I'm not involved in the work around proving this theorem. So I don't want to say yes or no. I certainly do not know the answer, and it could be known to someone. But that's just not me.
Yeah, not among the many hands of 2000.
I'm not one of these many hands. Yeah, none of my hands are part of those many hands. Yeah, exactly. Yeah.
But I also have a question, if I may.
Yeah, of course.
If I understood you correctly, you said that once you have an isomorphism of Elliott invariants, you induce star homomorphism between sister algebras, right?
No, yeah.
So how come that we have certain I meet it every now and then in proofs that, well, we cannot construct a star isomorphism between these sister algebras, but they have the same Elliott invariant, so they are isomorphic.
Technical question.
Yeah.
Okay.
Because,
can you repeat the question? What?
well, for instance, I remember a talk in Oslo of I forgot her name. But she argued that, all right, I cannot show you a star isomorphism between these sister algebras, but they have the same Elliott invariant, so they are isomorphic. So if indeed you can just induce a certain concrete star isomorphism out of a certain concrete isomorphism Elliott invariant, then you have some general recipe. So there shouldn't be such statements.
Necessarily.
No, yeah, it's a bit like when you show that two sets with the same cardinality admit a bijection between them. It's not really constructive, you know. Perhaps if it's concrete cases, if you follow the recipe, you can find something, but in the end, there's always an intertwining. There's a limit argument that just like in this Cantor-Bernstein argument, you know, you embed one into another one, the other one to this one, another to this one, and you go back and forth. In the limit, you get something. It doesn't come out with a closed formula, if you want. It comes at the very least, it comes out as a limit, but even that is probably it's actually more complicated than just that. But it's
okay. I didn't expect like explicit formula in terms of generators. I can give you another example. There's this beautiful alternative construction of a Jiangsu sister algebra due to Ian Putnam and collaborators. Where you construct some broken orbit foliation, whatnot. I cannot give you the precise and then they say, well, by checking Elliott invariants, we know that this is a Jiangsu sister.
Yeah, this is true. There's no, it's really not clear at all actually how to produce it. So already this isomorphism which exists between Z and Z tensor Z, no one knows an explicit formula or anything close to an explicit formula.
That's another example. You're right.
Yeah, it's it might but these type of things already happen with algebras that are easy to construct. For example, O2 tensor O infinity is isomorphic to O2. So these are the Kunz algebras. And I'm not sure that anyone has constructed an isomorphism. That anyone has constructed a map from the right to the left. Let's say, the right one, the one on the right has two generators. In principle, should be easy to say what they, this is certainly not the case, but one would wish that it would be easy to say what S1 and S2 go to in the left-hand side, perhaps a tensor product of generators.
Yeah.
But I think it's known that is not possible. Like a tensor, S1 and S2 here, it's known that they cannot go to a simple tensor of generators on the left-hand side. And actually, probably not even an algebraic combination of them. It has to be really something that appears in the limit. So it's really challenging, I think, in general. And it's probably not possible to give an algebraic formula of any kind.
Okay, so please forgive me, but I cannot resist this comment. You know that the O2 sister algebra is isomorphic to the graph sister algebra of a Kunz splice.
Yeah.
And here we have a beautiful explicit formula for this, which is completely elementary.
Yeah,
even though you don't have a close formula for this, it's strange.
Yeah. Some of them, it is true. I'm not saying that no isomorphism can be described with nice formulas. And with the Kunz algebras, there's some that one can do, and that I was trying to be careful, and I don't remember which ones can, which ones cannot. That's why I used O infinity, because I think for this one for sure not. But for some of them it's possible. This is true. But
because what is tantalizing for me, you have an obvious bijection injection from O to the Kunz-Splice sister algebra, but why on earth it's surjective? It's,
Right.
For me, it's incredibly fast.
Yeah.
And sorry,
So-
I have one more related question since you mentioned
Yeah.
this Cantor-Bernstein argument. So you can in fact somehow define what does it mean to satisfy this Cantor-Bernstein property in any category. So you could say that a category has this Cantor-Bernstein property. The following is true, that if you can embed one object A into the object B and also B into A, then A and B are isomorphic with respect in the corresponding category. So is it true that this property holds in this context of this sister algebras satisfying all these assumptions?
No.
No,
There are
okay.
sister algebras A and B. It's also not so difficult to construct
question.
this.
Not retraction.
Sorry?
No, it's okay.
Okay, so there are sister algebras A and B in this class that embed mutually into each other, but are not isomorphic.
May I sum up all these questions?
Yeah.
In a single question. So at the moment there is no constructive proof of the construction of this isomorphism.
No.
Is it does it rely on the fact that somewhere, for instance, axiom of choice is used, or is it some deeper reason?
I mean, certainly the axiom of choice is used in numerous places. That's gonna be one problem for sure. There's another problem that comes from the UCT that this is the UCT. If you go to the definition, it tells you that a map that is always surject. I mean, the UCT can be redefined as this. You start with a sister algebra, and there's a map defined at the level of K theory or KK theory that is always injective. And the statement of the UCT is this map is actually surjective, and the inverse satisfies this and this and that. And this is also a bit of a mysterious thing. Why? I mean, you magically get that it's surject. I mean, that it is it's surjective out of this property that is given to you. So the UCT is also one factor of mystery in these constructions and these proofs. For example, if very concretely, right? So if this map that is always injective, by the UCT is surjective. It allows you to pick an element. So for every element in the codomain, pick an element in the domain that hits it. But this is not. Okay, it's a baby version of choice, basically, right? But it's a choice that in general you will not be able to make without knowing the UCT. So it's So we're very far from any explicit construction for these maps, I think. I should also say I'm really not the right person to be answering these questions. I know that I'm the speaker that talked about this theorem now, but this if one of the many hands says something that contradicts anything I said, you should probably take their word for this. But I'm also confident that what I said is also not. In any case, so this is a theorem. As you see, it's very fascinating. There's a lot of questions. It's very interesting. And it has attracted a lot of attention since it's been finally proved, but also before that, a lot of people were trying to contribute to its proof and to its understanding. Now that we have it, it's also very interesting to know to which algebras it applies. And what I mean by this, because it's clear which algebras it applies to, these are the ones that satisfy the assumptions of the theorem. But what I mean is something a little bit more meta-mathematical, which is perhaps, you might be aware of many constructions where you take an object from perhaps a different field, like an algebraic object, perhaps a group, perhaps a dynamical system, a graph, and out of it, or tiling, out of it, you construct a C-star algebra. And these constructions are very popular. They're studied for many reasons by different people with different things in mind. And this is one of the things that I want to focus on today. I want to focus on C-star algebras that are obtained from dynamical systems. And the motivating question for us today will be, when is the C-star algebra that you get from a dynamical system, when does such a C-star algebra satisfy the assumptions of this theorem? So let me yeah, write some of these things down. We want to know which C-star algebras in interesting classes satisfy the assumptions of the figure. And you could, in principle, ask this for other classes as well. I will focus on cross products because that's, yeah, what I do. But you could also ask this for graph algebras. You could ask this for certain group product algebras. This would also make sense. Group C-star algebras never fall into this class. It's not obvious, but it's true. Higher rank graph algebras. So substitutes of the classification here. And we will focus on cross products. And so let me set up the stage. What cross products do I mean? I mean cross products by topological dynamical systems. So let G be a countable discrete group. My group G will always be countable and discrete, even if I forget to say it. Let X be compact metrizable. And again, my spaces X will always be compact and metrizable, even if I forget to say metrizable. Often it will happen. And let G act on X via homeomorphisms. Out of this data, this topological data, I want to construct a cross-product C-star algebra. The one denotes like this, C of X, semi-direct product G. There's in principle more than one possible construction. There's a minimal and a maximal one. The one that I will describe to you now in one line is the maximal one, just because it's easier to define. In the cases that I'm interested in, they all agree, so there's no real loss of generality. So the cross product is the universal C-star algebra generated by a copy of C of X and unitaries UG for G and G. So there's one unitary for each group element, satisfying that UG F UG star, which is the same as UG inverse, is equal to alpha G of F for every G and G for every F and C of X. I guess it should say to be very, let me just add it here. UG times UH is UGH. But the unitaries are not just any unitaries, but they form a unitary representation of the group.
I'm sorry, just a quick question. If your set X is just one element set, then this construction boils down to the C-star algebra of the group?
Precisely, exactly. So if X is exactly. So if the space X is the one-point space, and the action must be trivial, and this really gives you the universal group C-star algebra of G. There's also a reduced version of the cross-product construction that, in that case, gives you the reduced group C-star algebra. Yeah, exactly. In general, this is a super interesting construction. Even, I mean, also for, as you see now, for the trivial action, this is interesting, and for the not for interesting actions, it's also very important to look at. For example, the rational rotation algebra can be described as a cross product, as the cross product of the integers acting on the circle by the rational rotation.
I have a question. May I?
Yeah.
Are you interested in the following question? Looking at the Elliott invariant, can we decide whether we are in this class you described, or is impossible?
So you mean in the context of this theorem, if I give you an Elliott invariant,
Yeah.
so if I give you a C-star
Is the
algebra.
Elliott invariant of the class you described, just described, some special or it's
No, it
completely
is.
general?
It's completely general. It exhausts all the
Completely
possibilities.
general, okay.
Yeah. So what is also true is that every C-star algebra has the same Elliott invariant as a C-star algebra in this class.
Mhm.
Okay.
Yeah. So in some sense, this is the largest class that you can, I mean, in a very precise sense also, this is the largest class that you can possibly classify with this invariant. Yeah. So thing that I should have mentioned before. So this is kind of an, if you don't alter the invariant, this is an optimal result. With the possible exception of the UCT, which may be redundant, but surely the class is the largest possible.
But what about this class of cross products?
Then it's
What
not
about
so
the
clear.
Elliott invariant of this class?
You
Is it
have
special
to
or still completely general?
you have to prescribe the group, because then you could take the group to be if you just give me the invariant, I can always find like take the group to be trivial and find the algebra with that invariant. So if you prescribe the group, there are some restrictions. Certainly on the trace space part, there are restrictions. But on the K-theory, this is really not well understood, honestly. I think it's a major kind of conceptual problem that we have now. Understand the range. I mean, which C-star algebras are obtained via cross products in this setting? Which Elliott invariants arise via cross products by the integers or via cross products by the free group. It's not understood really. And it's really interesting to study. I don't think really so much has been done in that direction. There's partial results, but not systematic studies. Yeah.
So what you are interested in is rather a separate problem from the problem of classification. You are using classification to your problem, not you are want to say something about classification. Methods specific for cross products.
So in principle, I actually neither apply the classification theorem nor give so it's kind of like a. Let me just take the question. Perhaps I give a better answer. I think it will be clear if I state the question. So the question is, when does C of X cross G satisfy the assumptions of the theorem? And so in principle, my motivation is, when can I apply the theorem to a cross product? And this is really where my study stops, or like at least in this talk, this is as far as we will get. When are we in a position to apply this theorem to a cross product? Of course, as you very well say, once you know that you can apply it to a cross product, you have to be able to compute the Elliott invariant. Otherwise, there's no use. If you cannot compute the Elliott invariant, then the theorem is very nice, but will not help you so much. And this is a completely separate problem for which there are partial results, there are some methods, there is some machinery, but it's, I would say by comparison, less understood than this problem. So computing K-theory for cross products, in some cases has satisfactory answers, but in general, for an arbitrary group, this is related to the Baum-Kohn conjecture, for example, as well, with coefficients. So it's really in itself a major task, endeavor, and problem. And I will not go there. So I will really just stop at the question of when can I apply the theorem to this algebra, and how do I apply it is a question for the next talk, I guess.
Okay, so Baum-Kohn and Renault theorem is the motivation for focusing at this class.
Yeah.
Okay.
Right. Yeah. Okay, so if we want to decide when the C-star algebra falls into the classifiable class, we just go through the list of assumptions. I will just and see what we can say about them. So let me just list them again. So separability and unitality, these are arithmetic in this case, because of the assumptions that I made on the group and the space. So then we have nuclearity. This is not always automatic, but we know exactly when this happens. This is equivalent. So nuclearity of the cross product is actually equivalent to amenability, not of the group, but something weaker, of the action. Let me just define for you what amenability means for an action. So G acting on X is amenable if, but this is the definition, if there exists a sequence mu n of continuous functions. I will continue here. Mu n from X to the probability measures on G, which I regard as a subset of L1 of G. So then I get the norm from L1, such that the supremum in X is compact, of mu n G acting on X minus G acting on mu n of X is 0 for every G in G. Sorry, this it's not 0, but goes to 0. This depends on n, and as n grows, this goes to 0.
So sorry, for fixed X, this is a measure, yes?
Yeah, so when you fix a point X, mu n of X is a measure on G.
On G, okay.
Right, and the group G acts on the measures on G because it acts on L1 of G by convolution and electrization. And you're saying that if you compare the measure that you get on Gx and G times the measure that you get on X, asymptotically, these are the same. The norm of the difference, L1 norm of the difference.
Sorry.
So G acts on these measures via push forward, yes?
Yeah.
Transport as measure, okay.
Exactly. Which is the conceptually, it's also the convolution with the Dirac, measure.
Mm-hmm.
Right. So this is amenability for actions. I should mention every action of an amenable group is automatically amenable as an action. And because you can construct these mu n's from Fellner sequences on G if they exist. What is interesting is that this property is also satisfied for certain actions of certain non-amenable groups. For example, the free group acting on its Gromov boundary satisfies this property, although of course the free group is not amenable. So this happens for non-amenable groups as well. And it's automatic in the amenable case. So that's nuclearity. How about simplicity? So in the case of an amenable action, which is the only one that we're interested in really. So if the action is amenable, then we know exactly when the cross product is simple. This is equivalent to the combination of two properties, namely minimality and this n means simultaneous. So simultaneously minimality and topological freeness. This is a notion that we'll define in 2 minutes. Minimality is just the absence of non-trivial closed invariant subsets. So if you have a subset that is closed and invariant under the group action, it's either empty or the whole space. Topological freeness is a weakening of freeness that I will define just a few minutes. So let me just write definition to come. Then I also had the UCT.
I like to say that minimality means that orbits are dense.
Yeah, it's the same. Yeah, exactly. UCT.
There is at least one dense orbit.
Yeah.
That's weaker, actually. Because you could have, for example, if you look at the one-point compactification of the integers, with the canonical action of the integers by translation, there is a dense orbit.
Oh, yes.
But there's a fixed point, and that's
yes. Yeah.
The UCT in this context, as I mentioned, announced at the beginning, this is automatic for us in this setting, so that we don't have to worry too much about it. Automatic if the action is amenable, which we have to assume anyway, otherwise we're not in the nuclear setting. So, and the question that remains is absorption of the Jiangsu algebra. So Jiangsu absorption or stability. This is really the question. So let me just restate very briefly. When is a cross product? When is C of X cross G Z stable or C absorbing, assuming that the action is amenable, minimal, and topologically free. So these are assumptions. These are necessary assumptions for classifiability, the amenability, minimality, and topological freeness. And the question is, what else do we need to guarantee also Jiangsu stability? If we have to add anything at all, perhaps in some cases we don't.
So this is maybe a silly question, but nevertheless, let me ask it. So is it possible that this Jiangsu algebra itself would turn out to be some cross product, or?
Again, it depends on which, I mean, you have to prescribe the group.
For some group.
Sorry?
So I'm asking whether for some group, I'm asking whether is it possible to find a compact metrizable space X and a discrete group G such that product is this isomorphic to Z?
I think this is not known. I think it's actually not known.
No.
No. So there were some attempts to write it as a cross product by the integer, which resulted in this work that Piotr was mentioning before of Putnam, Strong, and Dealey, where they described it not as a cross product by the integers, but as a partial cross product of the integers, or what is equivalent. What he mentioned was this orbit breaking subalgebra of an action of the integers. So this question is very interesting. People have looked at it. I think it is difficult. And I don't think the answer is known, honestly. But certainly very, very worth looking at.
And what answer is expected?
I don't know.
Okay.
I don't know, honestly. I think it's known that it cannot be by the integers. Because I think this is true. Right. So the unitary, the canonical unitary coming from the integers would have to be non-trivial on K1. So I think for the integers it's known for kind of silly reasons that it cannot be. For other, I mean, if there is another group for which this is true, I don't think it's known.
So the word of group is very rich, yes. So
yeah.
One may never know. Okay, thank you.
Yeah, of course. The group has to be amenable. If it exists, it has to be an amenable group. This is also known because there is a trace on the Jiangsu algebra. But I don't know much more on that. Yeah. So I want to come to the definition of this property that I promised I would tell you. In fact, I will define 3 versions of freeness that are very closely related and whose the distinction between them is very important in this talk. So let me start with the one that probably most people know, which is just freeness. An action is said to be free if for every non-trivial group element, the set we have that the set of points in the space that are fixed by it, so the fixed points of this group element, is empty. So there are no fixed points of any non-trivial group element. Then we have essentially free, which means the following. It means that for every non-trivial group element, well, we don't necessarily have that this space, this set is trivial, but its measure under every invariant probability measure is 0. It is. So prob sub G of X are the probability measures for L, probability measures on X that are invariant under the action. And you see immediately from the definition that if it's free, then it's also essentially free. And topological free, or topological freeness, is like this. Again, the quantifier is that for every non-trivial group element, some set is small, and the set that is assumed to be empty in the first line is assumed to have empty interior in this case. So this is interior. So it could be non-empty, like the conjugation action on the circle has 2 fixed points. So it's not free, but it's the interior of the fixed points is trivial. So that one is topological free, but not free.
Sorry, just a general question. For
Yeah.
every measure mu in prob G of X, is it true that this measure on an open set would be positive? Or would
If
necessarily be
this is an excellent question, because you're already thinking whether 2 implies 3, right?
Mhm,
And,
yeah,
and exactly. And the answer is yes, if the action is minimal.
minimal. Okay.
Minimal, yeah. Because for the I think it's just a silly example, but for the trivial action, every measure on the space is fixed, but not every measure is positive on open sets. So, but if the action moves around the points a lot, then any invariant measure will have to be positive strictly positive on any non-trivial open set. So so the trivial action is kind of a counterexample for 2 implies 3 outside of the minimal case. But
Okay, thank you.
you're welcome. This is let me write down actually this observation that you were alluding to. It is clear that 1 implies 2, and also that 1 implies 3 is clear. And 2 also implies 3 if the action is minimal. Precisely because of what you just mentioned. If the action is minimal, every invariant measure has to be strictly positive on a non-trivial open set. And therefore, it's exactly. If it's 0 on that set, then the interior of that set is also trivial. Right. So we want to know, sorry that I zoom out. I know that I should keep it as big as possible. I just want to understand where I am. Right. Again, back to the question. The question is, when is a cross product Z stable? Assuming, among others, amenability of the action, minimality and topological freeness. Most of the work that has gone into answering this question has been in the case where the group is amenable, not just the action. Although there's some recent things done in the non-amenable case as well. So just to tell you what I'm going to do in the rest of the talk, I will give an overview of what is known, both in the amenable and the non-amenable setting, because the type of results, certainly the techniques, but also the statements of the results are quite different. And I want to give an overview of the things that are known, starting from the first results, possibly, and then getting to the the ultimate or the most advanced results that we have at the moment. We don't have a definite answer. I should perhaps already tell you this. We do not have a characterization of Z stability for cross products. They, differently from what happens for simplicity or nuclearity, these are completely understood. I mean, here's the exact characterization. We do not know. We do not have an equivalent characterization of Z stability in terms of dynamical properties. But we have sufficient conditions, many, in many cases. In some cases, also if and only if type results that I want to discuss. So most of the work has been done in the case where G is amenable. And actually, even when the group is amenable, most of the work really has been done assuming freeness and not topological freeness. And I would say actually, yeah, really almost all. I mean, with one or two exceptions, all of the results that are available are for free actions, and most of it assuming freeness, which, as we discussed before, is stronger than what one really needs. What one needs is topological freeness. This is kind of the minimal necessary assumption. Usually one assumes freeness. The reason why this historically has happened is that there are many groups for which 3, 2, and 1 are actually equivalent, specifically for the integers. A topologically free action of the integers, minimal, is automatically free. And since the integers were really the first group that was looked at from this point of view, doesn't matter if you assume freeness or topological freeness, so you might as well assume the stronger condition, work with it. And then these results started to be generalized, extended to other groups, Z to the D, groups of polynomial growth, groups where there actually is a difference between all these notions, but somehow what stuck was just assume freeness for the actions. Let me tell you perhaps the first result in this direction.
Can I ask you once more?
Of course.
And
of course.
Effective actions have not been studied. A weaker notion of effective action.
Yeah, so effective means that every non-trivial group element acts somewhere non-trivially. So for every non-trivial group element, there's at least one point that is moved by it.
Exactly.
This is weaker than all of these properties.
Yes,
because
probably than 1. Yes, weaker than 1 certainly, but the others I don't know.
Yeah, but for example, if you let's negate effectiveness. So there's a group element that fixes everything. Right? So
group element.
For that element, exactly, so non-trivial group element. For that element, this set is all of the space X. So its interior is also all of the space X and not empty. So effectiveness is actually a very, very weak condition. That is too weak to get to bring the cross product into a classifiable class. And it's implied by all of these ones. All of the actions that we talk about here are effective.
Okay, thanks.
You're welcome. So the first result in this direction, at least as far as I can trace it, of course, there were even more particular cases around the irrational rotation algebra. But the first systematic result is a result of Thomson-Winter. I think it was 2009, but it could be off by a couple of years. It says the following: if the dimension of the space X, and this I now mean covering dimension, is finite, and the action of Z on X is free and minimal, then the cross product with the integers is Jiangsu stable. I should also say that the group has the space has to be infinite, like it cannot be a finite set. But yeah, and what was done after this result was so there were a lot of attempts to generalize it, keeping this assumption, but going to more general groups. And there were many results in this direction. First for Z to the D by Gabo-Szabo, groups of polynomial growth. And now the most advanced result that we have of this kind covers all elementary amenable groups. So let me state it.
So Eusebio, just to double check. Are other assumptions of the classification theorem satisfied in this case?
Can you ask again?
Yeah, I mean, all the other assumptions of classifiability. I mean, the stability is one condition, but
Yeah, exactly. So as in this question, let me use a different color even. If the action is amenable, minimal, and topologically free, then all the other ones are automatically satisfied.
and here you are amenable because group is a minimal. You are
Exactly.
logically free because you are free. And minimality comes from where? It's assumed.
It's assumed there.
Okay, good.
Free and minimal. Exactly. So in this case, the other conditions on the action, we're actually assuming even slightly stronger things. The group is amenable, the action is even free. So everything else is guaranteed, and the cross product is stable. I should perhaps, I mean, let me just write, and therefore classifiable.
Yeah, exactly. Oh yes, thank you.
Yeah, because in this case, the stability is the only thing that remains to be checked. A result of Kerr and Narishkin, who 2021, I think it was, is the most advanced one that we have in this direction. It says that if the space X is finite dimensional, the group G is elementary amenable, and the action is as before, free and minimal, then the cross product is Z stable. And as Piotr just mentioned, this in particular implies classifiable because the other assumptions are automatically met.
What is elementary amenable?
Right, so elementary amenable, this is the smallest class of groups, which is closed under direct limits and extensions that contains finite groups and the integers. So what you do is you start with the integers and the finite groups, which is like kind of elementary groups, if you wish. What properties can you apply to amenable groups to obtain again amenable groups? Well, you can take direct sums, and more generally extensions, and you can take direct limits of amenable groups, and these are amenable. So the point is, with these operations, extensions and direct limits, all the ones that you can construct out of the most basic ones, which are finite and Z. And this class includes all abelian groups. Yeah, okay. It includes many groups for polynomial growth, solvable. I mean, and it was open for some time whether every amenable group is elementary amenable. So it was not known whether every amenable group could be constructed with these basic operations from finite and Z of free groups. And the answer is no. So there are amenable groups which are not elementary amenable. They're not so easy to construct, but also not not too bad. These are not like the non-exact groups of Gromov, but they exist. So this theorem doesn't cover all amenable groups. It really but it covers a lot of them.
So amenability of the action is not enough here. You must know something about the group itself.
Right, exactly. Yeah. So if you just know that the action is amenable, it's not enough. And actually, it's also not enough to know that the group is amenable. You have to know that it's elementary amenable.
Mm-hmm.
So even that, yeah. Mm-hmm. In a few minutes, I will tell you a few speculations of what probably is the case, and it's what you say it goes in that direction. What should be true, but what we know is just this for now. Again, you see that you have this assumption on the space, and it was people wondered at the beginning. Okay, is this assumption necessary? Do we have to have it? Can we get a Z-stable cross product with all the other assumptions? Z-stable, simple, separable, nuclear, unital, with a space that is infinite dimension? And the answer is yes, actually. But actually, before I tell you the answer is yes, let me tell you that because this is the way that it historically happened. If you drop the assumption of finite dimensionality, you may get something that is not Z-stable. So this is an example of Giol and Kerr. They show that there exist 3 minimal actions of Z on spaces X that are necessarily infinite dimensional, such that the cross product is not Z-stable. And I want you to compare this example, this statement, with the theorem of Thom's inventor, because they almost say the same thing, they almost contradict each other. The difference, of course, is that here we assume that the space is finite dimensional, and in the example of Giol and Kerr, the dimension of X is infinite. So what Giol and Kerr showed is that if you drop the assumption on the space, on the dimension of the space, and you're not careful at all, you can actually get something that is not Z-stable. Then, as I mentioned, the question was, well, can we ever get something that is Z-stable if the space is not finite dimensional? The answer to that is also yes. So, and this is a theorem that I was just about to state. Elliott and New, they show that if you have an action of the integers on a space that is not necessarily finite dimensional, but so that the mean dimension is 0, I would just write in parentheses, this is implied by dimension of X being finite. Let's say free and minimal also.
What is this mean dimension?
I'll tell you in a second. Then the cross product is Z-stable. In 1 minute I will define it, but let me just conceptually talk about this result. So this result tells you that finite dimensionality of the space is not strictly necessary to get a Z-stable cross product. You can get away with a little bit weaker, which is this mean dimension 0 assumption. So this is an assumption. This is automatic if the space is finite dimensional, but it happens also in situations where the space is infinite dimensional. What it is, so this is a notion. This is actually a very interesting connection to topological dynamics. Mean dimension 0, mean dimension in general, was defined by Lindenstrauss. In his work in topological dynamics, he didn't have anything with C-star algebras in mind when he looked at it. Probably perhaps did not even know much about C-star algebras. So let me tell you what it is. Let me make sure that I don't get it wrong. It's somewhere. Yeah, I know where it is. This I usually work with an equivalent characterization of mean dimension 0. Then I will tell you in a second. It's easier to state, but it is like this. So the mean dimension of an action of Z on, let's call it H, because it's a homeomorphism on a space X is like this. The supremum over U will range over all the open covers of X. The limit as n goes to infinity of 1 over n times d. This is usually called the order. Perhaps order is better too. Order of the following cover: U, wedge h of U, wedge h to the n. Perhaps to normalize it's better. Let me tell you what these things are. So h of U is just, if you start with an open cover, you just look at the images under the images of all the open sets in the cover under the homomorphism. So that's h of U.
So
And-
wait, so the space supremum is over elements of some open cover or over all open sets?
all open, over all open covers.
So this is open cover.
Yeah, exactly. I mean, in this format, there's no individual open sets. So H
Okay.
of curly U is really the open cover of X, whose elements are H of an open set that belongs to curly U. Yeah. And the wedge,
Those are families, yes, families of open sets, yes.
yeah, exactly. So H of curly U is a family of open sets. Yeah. Yeah, exactly. Then the wedge is the common refinement. So you intersect, if you have two open covers, what you can do is you intersect the elements of the cover. You call this the wedge of these two covers. This is again an open cover because you intersect finitely many open sets. It's a common refinement, if you wish. You can do this with finitely many. This is what we're doing here. So I just have to tell you what the order of a cover is. So the order of a cover, let's call it V, is the smallest number of overlaps of elements of V. So what this is when you cover a space by open sets, some points of your space will be in more than one at the same time, necessarily. And you look at the smallest number, -1 or +1, depending on how you index things. So it's really, you're counting overlaps. It's not really important exactly what it is. What is important is that this part here is always bounded by the dimension of X. The dimension of X is essentially defined using orders of open covers and common refinements and things like this. So, right, so if that part is finite, since you're dividing by n and taking the limit as n goes to infinity, that's going to go to 0. And this heuristic argument at least shows that if the space is finite dimensional, then the mean dimension of the action is 0, regardless of the action. Actually, every action on a finite dimensional space has mean dimension 0.
Sorry, this whole definition is the definition of the dimension of the action. So it could happen that X is infinite dimensional, but still the action somehow only sees this part which somehow resembles something which is finite dimensional. So you are moving
Exactly.
in the direction of something which is finite dimensional, yes?
Exactly. Yeah.
Like that, okay.
Yeah.
Mm.
Right. I should speed up at least a little bit.
Sorry, can you give me an example of an order? I mean, I'd like to see a cover and its order.
Yeah. So what you can do is, for example, if you do an open cover of the, let's say, the unit interval,
Yeah.
I will cover it. I mean, let's say that you want to cover it with two open sets.
Okay.
This one is 1, and the other one, I mean, they cannot be disjoint, because if they're disjoint, you're missing a point. So they have to have some overlap. So these points here, they belong to two open sets. So now the overlap number or the order of this cover is 2, because it's kind of the overlap, 2 sets of it. And then you always have to subtract 1 to obtain the dimension.
Okay, I just want to understand the phrase overlaps of elements. Okay, now I understand.
Yeah.
Okay, thank you.
You're welcome. Yeah, so this is really kind of model after the definition of covering dimension of a space with open covers, refinements of open covers, and the order of refinements of open covers. But yeah, so you have to look at all the elements of your space. You count for each element of the space, you count in how many elements of the open cover that point is. For some of them, it will be 1, but for some of them, it will be more than 1. You look at the maximum of all of that, and you subtract 1. So in this case, I mean, this point belongs to only one open set, that's fine. But these ones belong to two. So the maximum is 2. You subtract 1, and that's the dimension. In this case, the unit interval has dimension 1 because of that reason. Any open cover has order 2. Yeah.
Your definition looks quite general, so it doesn't not necessarily be only valid for Z, yes? You could also take
Exactly.
another, yes?
You could take another amenable group and use Fulner sets. So instead of like taking these powers of H, you take the images of the Fulner set of your action.
Okay.
You divide by the cardinality of the Fulner set. You could do that. In principle, you could also do this for Sophic groups, although I'm not sure if anyone has done that. But in general, I mean, for an arbitrary group, it's not clear how to do it.
I see. So the fact that you are taking those powers is corresponding to the fact that you deal with this group being equal to Z. Okay.
Exactly. So this is, I mean, in this case, the powers that you're taking there of H, the numbers, they're part of a Fulner set. That's really in the end what is happening. Yeah.
Okay, thank you.
Yeah, of course. So let me tell you what is believed is it's going to be the case, the outcome in the end. This is a conjecture. I don't want to attribute it to anyone because no one has stated it in this form, but it's certainly weaker conjectures have been stated that in combination are equivalent to this one. So this is a combination of conjectures in the literature. Let G be amenable. Acting freely and minimally on X. I'm not assuming that X has finite dimension. If the mean dimension of the action is 0, then the cross product is conjectured to be Z stable. And let me just, right, okay, so there you can see one confirmation of this conjecture is this result of Elliott and New, which says that the conjecture is true for the integers. Yeah. Since then, more cases have been established. Jean New did it for Z to the D. Let me tell you the most advanced result in this direction. This is a combination of Kerr and Kerr-Narishkin. Should be really careful now. I should be really careful. This. If you forgive me for starting the statement, I will finish in a second. But I want to say one more thing. This condition of mean dimension 0, which is entirely topological, has been studied from people in dynamical systems. It is conjectured to be equivalent to another property of dynamical systems. The conjecture not by anyone in C-star algebras. This is their conjecture that is still working on. Conjecture to be equivalent to the so-called small boundary property. In the small boundary property for a dynamical system is there exists a basis of the topology consisting of open sets whose boundaries have measure 0 for every invariant measure. So this is a notion of smallness that you can talk about. If you don't say invariant measures, I mean a set that is 0 under every measure, it's just empty, because you can take direct measures. But if you declare that it be 0 under all invariant measures, then you get a notion that it's non-trivial. This is called a small boundary property. And it is conjectured to be the same as mean dimension 0. It's known for some groups, not in general. But possibly for all elemental groups, it's going to be the case. So the result of
Sorry, this conjecture is in this context of groups acting freely and minimally, yes?
yes. Yeah. They showed that if G has polynomial growth, kernel is polynomial growth, and so the action has the small boundary property, so this property that I just told you about, that is conjecturally equivalent to mean dimension 0, minimal and free, then you get Z stability. So for groups of polynomial growth and up to taking the conjecturally equivalent notion, this is known. I want to rectify a little bit the authors that I attributed this to. So this is Szabo, and also Narishkin had a separate paper where he contributed to this. I think this is a correct attribution.
So sorry, so taking this theorem into account, this suggests that at least this SBP is as strong as this, yes. Somehow it appears from the content of this theorem as a stronger assumption, yes, since this is enough to conclude that this cross product is stable, yes.
I would agree. I agree that it would appear to be stronger. I think at the technical level, it feels different actually. But mean dimension 0 is it's just difficult to work with in connection with cross products. There's essentially only one way that we know how to use it in cross products, by the ways of comparison and things like this. It's difficult. It's actually difficult. And small boundary property, it's this easier ways to connect it to the cross product, which I agree would make it seem like it's a stronger property, but it's just actually a property of a different nature that is closer to C-star algebras. This is how I would describe it. Really.
Okay, I see. So it is possible that you have notion which is not necessarily stronger, but it is somehow easier to work with.
It just fits better. Exactly. Yeah, it just fits better.
Okay.
Yeah. I have a question. Do people assume in this expected equivalence between these two blue assumptions that these invariant measures must be Borel? At least.
Yeah. So these are Borel measures.
Otherwise, I cannot see even a relation between these two conditions.
This is supposed to be Borel measures on X that are invariant under the action. Yeah. Yeah.
Do you mind reminding us what polynomial growth means?
Yeah, okay, I can do it verbally.
Yeah.
So what you do, these are finitely generated groups. I should have written here. This is finitely generated. Then you can look at the Cayley graph of the group. So the vertices are all the elements of the group, and there's an edge between two elements in this graph if the corresponding group elements differ by an element of the generating set. So what you do is you fix a generating set. From this, you get a graph. And there's a definition of the growth of a graph. So it's basically so you have to count how many elements are at distance at most n from the unit, and you look at the asymptotic behavior of that, maybe divided by n. In polynomial growth, actually, no, without dividing by n. So you just look at the ball of radius n or r, the cardinality of the ball of radius r, and you say that it's polynomial growth, if if this, as a function of R, is below a power of R, fixed power of R.
It's a growth of the length function.
Exactly. It's a growth of the length function in the Cayley graph of G. It is a theorem of,
example of something which is not of polynomial growth.
something that is not a polynomial growth.
Yeah.
The free group.
Okay.
The free group. So it is a very, very, very deep theorem of Gromov that groups of polynomial growth. So polynomial growth is equivalent to being virtually nilpotent. Virtually means that you have a finite index subgroup that is nilpotent. So in particular, these are all amenable groups. Actually, relatively small, if you wish. So Z to the infinity. Okay, it's not finitely generated. It's all, you cannot even talk about that. But if you could define the growth of Z to the infinity in some way, it would be not polynomial. So the growth of Z to the n is like the nth power. So R to the n. And maybe it could be that Q is also not, yeah. But the free group is a typical example of a group that is not of polynomial growth.
Yeah, thank you so much.
Yeah.
Yes.
Yeah.
And maybe
So this-
it's also worth mentioning that there are groups which are of intermediate growth. Something is
Right.
in free group is exponential growth, but there
Yes.
are example which is something in between exponential and polynomial.
That's true. That's true. These are difficult to construct, of course. Yeah. But yeah.
Mm.
Yeah, exactly. That's true. Right. But let me rewind a little bit in the story that I was telling you. I told you that most of this work has been done assuming that the group is amenable, and actually that the action is free. Right? And we saw, I try to convince you that the natural assumption in this context is topological freeness, because it's a minimal one that you need for classifiability. And so with some of my collaborators, and I will scroll up a lot, so sorry for that. My collaborators are, for the theorem that I will mention now, are Shirley Geffen, Rafaela Gessing, Grigorios Kopsahelis, and Peter Narishkin. With them, we were interested in exploring these questions beyond freeness, in the understanding that freeness is, okay, for sure, super important case, and most of the difficulties are already there, but ultimately you should try to go further. And we were able to obtain a version of this result without freeness and just with topological freeness. And actually the statement is the same. So let me say this is me, Geffen, Gessing, Kopsahelis, Narishkin. This is not out on the archive yet, but it will probably soon be out, perhaps within a month. So 24. Same as above. If one just assumes topological freeness, which is the minimal assumption that you need in this respect. So this is very satisfactory for us because it tells us that there's really nothing about freeness that will break down if you weaken it to the natural assumption in the setting of topological freeness. And this is also the amenable case. Let me very briefly discuss the non-amenable case, which is actually very interesting as well. For this, I want you to keep in mind that the amenable case was the first one to be treated, right? And they realized mean dimension 0, you have to have it, otherwise you might fail. So there are cross products that are not Z-stable. Things get complicated if the space is infinite dimensional. And in the non-amenable case, nothing very systematic had been done until recently. There were some isolated classes of actions for which it was known that the cross product was Z-stable. Let me just write for non-amenable groups. So in principle, one would expect things to be at least as bad or complicated or wild as they are for amenable groups. You would not expect non-amenable groups to now all of a sudden be nicer than amenable groups. And this is why I think this result is very surprising at first sight. For non-amenable groups, things are actually nicer. And okay, nicer, this is really, of course, very subjective. What I mean by nice is very relative. And what I mean, let me just tell you what I mean. So this is the other result that I have with Geffen, Julian Kranz. So Gardella, Geffen, Kranz, and Narishkin. This is already from a couple of years ago. If G, let me just say for now that it's a hyperbolic group. And if you don't like a hyperbolic group so much, just think that G is a free group. We don't know this for every non-amenable group, but we would know it for a large class, certainly containing hyperbolic, but more. And G acts on X minimally and freely, and topologically freely, which are minimal assumptions in this case, and amenably, of course. Then, so what can one say? The assumptions that I already listed are the minimal ones that guarantee that the cross product is simple, separable, unital, and nuclear in the UCT. So these are the minimal ones that guarantee that all of the other conditions are satisfied. And also they also guarantee in this setting that the cross product is Z-stable. And the surprising part, and what I meant by things are nicer in this setting, is that there's nothing that one has to assume about the space being finite dimensional. The action have some kind of mean dimension 0. Small boundary property, this is just always true regardless of the action. As soon as it is amenable, minimal, and topologically free, which are the minimal conditions anyway that you need to have. The conjecture that we have in the setting is that this is not just true for hyperbolic groups or the free groups. This should be the outcome in full generality in the non-amenable setting. So if G is non-amenable, G acts on X amenably, topologically freely, and minimally, then the cross product ought to be Z-stable. And I want you to contrast this with the conjecture that I stated before, which had the mean dimension 0 or equivalently the small boundary property. It had an extra condition that is not always satisfied. This is what the example of Giola and Kerr showed to us. This assumption is not always satisfied, and whenever it's not, you may fail to be Z-stable. Already for the integers. And what it turns out is that in this setting, there is just nothing like that. This will not happen. For the free group, for sure we know it for a fact. There are no wild actions of Fn leading to non-Z-stable simple nuclear cross products. And this was a surprise for us, I think. Yeah, so I had a few more things to say, but I think this rounds it up well. Yeah, so I thank you very much for your attention.
Thank you so much. Well, today is the International Day of Happiness, so I have no choice but to tell you that I'm extremely happy about your talk.
Thank you very much. I'm happy.
I'm
extremely happy that it was well received.
Yes, and also this is a Persian New Year, and we had here one participant from Tehran, so she's probably gone now, but okay, she celebrated the New Year by listening to your talk.
Okay, oh, nice.
But now, I'm sorry, I cannot resist but to immediately ask you some questions. I know it's rude of me, but could you please come back to one of your main results where you had this theorem where things are stable and
yeah. I will scroll. I will scroll slowly and you just tell me to
Yeah.
stop.
Yeah, yeah, up. Up, wait. Yeah, I think let me concentrate on Tom's winter, okay?
Yeah.
So how about the following situation? You see, for starters, what I want to do, I want to replace your commutative sister algebra by a unital sister algebra. And now let's see of what your conditions are. So, okay, I have a unital sister algebra, so I'm compact. I take it separable, so I'm metrizable. I take it of finite nuclear dimension, so I have finite covering dimension. I can take a free action. We know very well what a free action means
Still of Z.
Yes, still of Z. Yes. Although of Z, oh, wait a second. Okay, locally compact is also fine. We know what the free action means. And then, you know, can you still tell us something about this result? Is it stable? I don't know. Take something like the rational rotation sister algebra itself, and then act with some, you know,
Yeah.
Z squared.
Right.
Really, and it's also
So-
minimal. Ergodic. It's
Right. So there are many results in this direction. Yes, many positive results. They typically assume that the algebra A is simple, which is kind of the opposite end of the spectrum, right? Because
exactly. Yes.
but somehow the thing is the techniques that you need to use to work with commutative C-star algebras are very topological in nature. And okay, if you want to extend it further, I mean, it's reasonable to start with the opposite end and see if you can do something there, and then try to come back together in the center, in the middle of the two extremes. So that what has been done is, in the simple case, the techniques are extremely different from the commutative ones. So it's at the moment very unclear how to marry them and get something that get a single result that covers them both. Even that is not clear yet. But so what is known is, let me just scroll up to show you the theorem. If you have a C-star algebra satisfying the assumptions of the classification theorem, and you have, so this is simple Z-stable, so a very nice C-star algebra, very far from commutative. But okay, let's just take that for now. And if you have in fact, an amenable group, or let's say the integers, just to be clear, if the integers act on it with the suitable versions of freeness, with a suitable version of freeness, then the cross product is Z-stable again and classifiable and has everything. So, okay, I realize that I'm not telling you the specific assumptions, the specific details, but this question in the simple setting has also been looked at, specifically simple and classifiable setting, and there are positive results. They're not as far-reaching as they are in the commutative case. So the groups that we can deal with in that setting are more restricted. But yeah, for sure, this is also a very interesting question. When is the classifiable class closed under cross products?
Yes.
Yeah.
Okay. Perfect.
Yeah.
And
I guess.
Yeah. No, go ahead.
I guess the next step would be to look at cross products by quantum groups.
That's my next question.
I knew I was gonna come. I know you so well, Piotr.
Yeah.
And this, I think that there's essentially nothing known.
Okay, nothing. Okay, so now I can ask everybody else to ask questions. Adam, fire at will.
Could I just ask, is there any connection between this mean dimension 0 and topological entropy? They both count somehow how the complexity of the action changes as you move open sets around under the group action.
Yeah, let me think. I think there is some connection, but it's very, very, very weak. It's not a rather. I mean, what I think the connection was is that the topological entropy has impact on the structure of the cross product. What exactly the implication was on the structure of the cross product, I don't remember it. Because you can have, I think you can have positive entropy even if you have mean dimension 0. Could that be? In any case, so I don't know for sure. I don't know the answer. I cannot give you a precise answer. I think topological entropy has been looked at in this context to try to relate it to some properties of the cross product. But exactly what they have looked at, I cannot remember.
Okay, thanks.
Okay, thank you. Adam?
Yes, I would like to ask you about this example, this infinite dimensional example, which this cross product is not z-stable. So could you describe the space X? Yeah, this example of Groll, yes, and Kerr.
Yeah, Jonathan. I can describe it to the extent that I can tell you that it's infinite dimensional. It has a Cantor factor. So actually, there's a surjective map to the Cantor space that is equivalent with respect to the action, where on the Cantor space you have an odometer.
What? Sorry, excuse me.
An odometer.
Odometer action.
An odometer action, yeah. So it's yeah, you can think of, for example, you can identify the Cantor state with like just a 2-point space, 0, 1, to the power n of the natural numbers, and the homomorphism is like add 1 mod 2, basically, or something like that. So this is an odometer, and but I don't remember much more.
But the Cantor set is 0 dimensional, so I'm a little bit puzzled.
Yeah, but this is only a factor. It's only a factor of the space. So it has, I mean, it subjects onto this.
So the space is infinite dimensional, therefore big, but also very disconnected, yes?
Right, exactly, yeah.
Okay.
If you want to look at the explicit construction, I mean, they only have one paper together. So if you look GIOL, so this is GIOL and Kerr, KERR. I think there will be only one match for that combination of authors.
Okay, thank you. So I mispronounced this name. Sorry.
No, it's okay. I noticed that's why I spelled it. But I think if you want to look at it, I think it's probably also nicely written.
Okay, thank you.
Yeah.
Any more questions from the
Yes,
Zoom?
I have.
Wait. Any more questions from the Zoom? I don't see any volunteers, so now from the room, Tomek.
Okay. Could you explain why in non-amenable case things are nicer?
This is a good question. I mean, it's unclear what, I mean, this is unclear to me. I think one heuristic justification is that there are just not so many amenable actions of non-amenable groups. And the very few that exist are very nice. This is, yeah, okay, it's a meta-mathematical answer that I'm giving you, right? So it seems like they're not so many, and the ones that exist are very regular. I think, but also at the technical level, it just seems like amenability for these actions is a strong condition, actually, which in the amenable case for the group, for amenable groups, every action is amenable, and that is not really an assumption. So what I told you earlier, when I told you, every amenable group, so every action of an amenable group is amenable, and there are amenable actions of non-amenable groups, probably didn't feel like assuming amenability for an action of a non-amenable group was a strong condition, but it seems like it is, actually. It seems like it imposes a lot of restrictions. So many that there are no wild actions with those properties. I unfortunately cannot give you a better answer. I also don't understand why things are nicer in this setting.
But it's a good answer anyway.
Yeah. But if the argument is that there are much more good actions of non-amenable groups. So the argument is from the typical behavior of this. So can we say that the typical behavior is nice?
Yeah, I think so. I think that the other thing is that there are just not so many examples of amenable actions that we know for non-amenable groups. So we know that they exist. We know that every exact group admits at least one amenable action, but they're hard to. We don't know many examples of them. For example, for the free group, if you want to construct an amenable action of the free group, I'm not sure that there's many constructions known that don't, in some sense, use the Gromov boundary action. So it's kind of like you have this very natural one, this model action, this kind of model, and the things that we know, they're kind of constructed using it. So there's essentially no other method to construct them. And it could be that there's really just not so many. And okay, this one is very nicely behaved. So if all the ones that you can construct start from this one, then all the other ones will be nicely behaved as well. It seems like to be the case. And what we see in this result matches that speculation, that there's perhaps not so many more. Again, I know that what I'm saying is not very precise or mathematical, but the feeling that I get.
Okay. Thank you.
So let us thank Eusebio again for an extremely brilliant and beautiful talk. Thank you so much.
Thank you very much all for being here.
Let me stop recording, but don't go away.